And so to start our study of intermolecular forces, IMFs, we're going to start by first looking at the most common, right, the one that every single substance has, London dispersion forces. And the first thing that we want to do is we want to ask the question, what is a London dispersion force, right? And why is it that every substance has it, okay? So a London dispersion force is often referred to as an induced dipole moment. Okay, big fancy words. Let's break that down. And so let's start with this idea of, so what exactly do we mean by an induced dipole moment? Okay, and so to help us, what we're going to do is that let us picture a simple atom, right? So imagine, if you will, that this represents my nucleus of the atom. Around it, you can see that there is the electron cloud with the electrons zipping and flying about, etc., etc. But here's what I want you to do. Think back to when we spoke about electron clouds. Was an electron cloud a solid, definitive space where the electron had to exist? And the answer is no. It was a probability cloud. Now, usually, typically, our probability clouds are going to be evenly distributed around the nucleus. What that means is most of the time the electrons do in fact repel each other, try to get as far apart from one another, and as a result, most of the time we're going to see this, right? We're actually going to see the electrons separated from one another. But does that mean that they have to be, that it's always going to look like that? And the answer is, of course, no. What I mean by that is that it is possible that at a given moment in time, by sheer random coincidence, probability if you will, right, there is a chance that I could find the overwhelming number of electrons to be on one side of a particular atom. And the same way that I'm calling this an atom, I could call this some type of molecule. But it is possible, right? It's possible that at a given moment, all the electrons, for whatever reason, they're all over on one side. Now, if I had to predict what's going to happen a moment from now, my guess is that a moment from now, those electrons are going to probably move to the other side or repel each other. But at this particular moment, at this instant, what we find is instead of having all of those electrons uniformly around my nucleus, now if I place my nucleus back here, what I find is that overwhelmingly most of the electrons are to one side, which means that I start to notice the positive nucleus of the positive nucleus of the atom peeking out on the left, and over on the right we see that we have all of these electrons giving this momentary or this temporary dipole. We actually create a temporary dipole moment. Now, the way it probably looks a little bit more is going to be what I have here, which means that I'm still going to have my nucleus over here on the left-hand side, but now overwhelmingly I have most of the electrons off to the right. Now, why is that a big deal? Well, if we had a single atom or a single molecule operating in a vacuum, right, then we wouldn't care. So what that it did this for one moment? Yeah, I'd agree. So what? But rarely do I have a single atom or a single molecule. In fact, most of the time when we're doing chemistry, we probably had a bunch of atoms or a bunch of molecules, and they were occupying a similar space. They were in the area of one another. Well, why is that a big deal? Because when one atom or one molecule undergoes this temporary dipole moment, there's probably in the very near vicinity another molecule or atom. And this molecule or atom wasn't skewed. This molecule or atom had its typical nucleus with an evenly surrounded electron cloud. But what's happening? Because the atom on the left has now undergone this temporary dipole moment, because for a moment it shimmied, right? It shimmied the electron cloud to one side. then now all of these electrons are literally racing at my atom on the right. And since all of those electrons are being kind of shoved over there, or all of that negative charge is going to be shifted in that direction, then what's going to happen is a split second from now, this yellow atom or this yellow molecule is going to be induced into creating a dipole moment. So again, we started off by saying that LDFs were the same thing as saying induced dipole moments. This is where the induction takes place. The purple one forced the yellow one. And so what we see is that while the purple one has had a temporary dipole moment and shifted, as the purple one goes back to its normal, regular looking self. So as the purple one goes back to its normal self, well, guess what? Over here on the left-hand side, over here on the right-hand side, my yellow one has now been skewed. And so this is what we mean when we say London dispersion forces or temporary dipoles, or more accurately, an induced dipole moment. What's happening is that every atom and every molecule has a chance, has a random possibility at any given moment in time to have its electron cloud skewed to one side. And when that happens, it alters or it affects, right, the other substance, the other atom or the other molecule. Now, if you sit there and you look at this, you go, okay, got it. So these like LDFs, these London dispersion forces, they're kind of like this wave-like phenomena, right? It should be kind of like, well, one affects the one, the left one affects the right one, and then now we start to kind of play telephone, or it goes like a train down the line. How strong could these LDFs really be? How strong could these London dispersion forces really be? And the answer truly is, well, it depends. And it depends on, you guessed it, size does matter. It's going to be critical to see how far of an electron cloud skewing, let me rephrase, how big of a dipole moment can a particular atom or molecule create. What we find typically is that the bigger the atom is, or the bigger the molecule is, the stronger the London dispersion force will be, because the larger the atom or molecule, the larger its electron cloud will be, and the larger that electron cloud is, then the greater it has the possibility of skewing, right? Or the stronger of a dipole moment it could create. What do we mean by this? Well, let's take a look. So down here over on the left-hand side, you'll see that I have my small atom and my big atom, or my small molecule and my big molecule. Again, don't worry about, these are polar, non-polar. Just pretend that that is literally an electron cloud and it's uniform. We're trying to keep this simple. What I would notice over here on the left-hand side is that when I look at my nucleus, so let's suppose that there's the nucleus, right? When I look at this molecule, what I'm going to find is that if I place my new atom skewed, or my new electron cloud skewed as far to the right as I can make it, right? We notice that originally this would have been my electron cloud, right? And when I went and I skewed it, this became my new electron cloud. Well, that means that an electron, sake of argument, that was over here at this valence position, at most at this point might be over there. Now, is that a dipole moment? And the answer is yes. Did the cloud skew? And the answer is yes. Well, did it skew a lot? And the answer is not so much, right? Yes, you're still going to have the nucleus poking out on the left-hand side. You now have more electrons on the right-hand side, but my guess is that this is not going to be a significant number of electrons on the right-hand side. It's not like there's a significant number of protons, sake of argument, left in the nucleus. So while this would have a London dispersion force and this would create, for a moment, a temporary dipole, it's not going to be a very strong temporary dipole. Now, why do I say it's not going to be very strong? Well, now let's take a look at this big guy here. And if I take this guy and I now do the same exact trick, let me actually put him over to the left-hand side. If I now do the exact same trick, right? And so again, let's go ahead and put the nucleus in the middle of all of this, right? So let us pretend that the nucleus originally was right here. This would have been dead center in the first one. It's still, right? The nucleus hasn't moved. What you should be able to see, and what becomes very obvious, is that now, if originally there was an electron here, look how much further with that skewing, right, with that dipole moment, look how much further that electron has shifted. As a result, since the electron cloud has shifted more, that means that we probably have a heck of a lot more electrons that can be over here on this left-hand side, which means this is going to be a more negatively charged pole, and that means you probably had more protons over here, which means that as the nucleus peaks out, it's going to be a more positive pole. Since the disparity between that negative and the positive charge is going to be larger, this will have produced a greater dipole moment, right? And so the bigger an atom is, the bigger a molecule is, the stronger the LDFs can become. And a lot of times students, when they're first learning about LDFs, think, oh, everyone's got them, they're super weak, it's not a big deal. But if we take LDF to the extreme, they actually can become a thing, and they actually can become quite powerful. So an example of ridiculously strong London dispersion forces is what I have over here, a good old-fashioned strip of Velcro. Now if you look closely at the strip, you'll notice that Velcro kind of has two parts to it. On one side it has these teeny tiny hooks, and on the other side, for lack of a better word, it's got this fuzzy area, right? And if we look at Velcro under a microscope, we're going to see something that looks similar to this, where you have the fuzzy area kind of interacting and trying to entangle itself amongst the hooks, right? What a lot of people will get confused about regarding Velcro is that they'll look at it and they'll say, well, we have this hooking system that is what's keeping the Velcro together. But in reality, Velcro is nothing more than these long polymer chains of atoms, right? It's basically a bunch of carbon atoms in a very long macroscopic amounts, right? So you can actually see them, right? But it's the same carbon chain or same carbon pattern repeating. And as a result, when we look at Velcro, especially like the fuzzy area of Velcro, what we notice is that it has a ridiculously high surface area. Well, if I have a high surface area, that means that I'm going to have a whole lot of space for electron clouds. And the larger my electron clouds are, the more they're going to be able to shift their dipole, even for a moment, which means that the London dispersion forces become much stronger. If I get a very large strip of Velcro and I slap it onto another piece, then it is very challenging to separate the two. Now you might be sitting there going, well, yeah, because everything hooked in. But it's not the hooking part. It's not a mechanical function. This is happening at the atomic level, and it is the London dispersion force. All of those temporary dipoles oscillating back and forth and back and forth and back and forth, all of that happening causes, for a moment then, right, for those two substances to be very sticky onto one another. Right? So London dispersion force is typically ridiculously weak. Like, who cares? They don't do a darn thing. But when you do take them in this massive quantity, such as Velcro, or another place that we see LDFs is that if you ever notice, like if you've seen geckos that can climb up any surface, right? What we've done is when we've studied their actual foot pads, we see that just like Velcro, there are all of these thousands and millions of microscopic little hairs that as they press on a surface, all the LDFs kind of kick in. That's what allows them to cling. And then as they kind of peel their hand off or peel their foot off, then all of those LDFs stop, right? And so they kind of like one at a time start to break the LDFs, and then they put their foot pad down again, and that's how they climb. But this is an example of where London dispersion forces will become a thing. Typically though, not so mission critical. So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.